Hi, let's start. Okay, so welcome to tutorial 4. Today we're going to be talking about convolutional neural networks, building on what you saw in the previous tutorial about MLPs. Okay, so specifically what we'll cover, we're going to talk about convolutional layers in deep networks, what they are, how they work, pooling layers. We're going to show some examples of network architectures. We're going to talk about fully convolutional networks, and we're going to show a specific architecture called a residual network. And again, we'll show implementation examples using PyTorch. All right, let's start. So first, just a small recap about MLPs, what we saw in the previous tutorial. Okay, so in the MLP model, this is the MLP model which we saw in the previous tutorial. I remind you that we have multiple layers. Each layer is composed of multiple neurons or perceptrons in the more technical term, which is what you see here. And in the regular MLP, each layer is a fully connected layer, which means that each neuron in each layer is connected to all the outputs of the previous layer. Okay, so formally we wrote it like this. We said that the output of the layer J depends on the output of the J minus 1, of the layer J minus 1. We have a matrix of parameters because the rows of this matrix are the parameters of each individual neuron in the jth layer of the MLP. And we have a vector of bias terms. Okay, so here again the input and output are vectors because we have multiple neurons in each layer. Okay, and like we said, these are fully connected layers. Okay, we saw that the MLP computes a nonlinear function of both the weights and the inputs, and that it can be used as a universal approximator. Given enough neurons, even with just two layers, you can approximate almost any function. At least there's a theorem that states that, which was proven a long time ago already. Okay, so what we saw were two applications of the MLP. We saw a regression application where we implemented everything from scratch. We used the quadratic loss, and then we saw a different application of classification of images where we used cross entropy. So now we'll take the same application of classification, and we'll show how to do the same thing, but this time with a new type of network called a convolutional network. Okay, so that's what we saw. But first of all, some motivation about why we were kind of limited by what the MLPs can do, why we would want to do something else. So first of all, remember that we specifically stated that it's each layer in the MLP is fully connected, which means each neuron in each layer is connected to all the outputs of the previous layer. So for example, if you have an image, it would mean that you're, like we did last tutorial, we took our images, we created a long column vector from each image, and then we just used that as features. Every single pixel from our image was a feature. Okay, so the problem is that it doesn't scale very well, because if you take this example, then let's say you have a 28 by 28 MNIST image, then each neuron in the first layer has to be connected to all those pixels, okay? But usually that's a very small image. If you want to work with kind of real world images, then you have much larger images and you have three color channels. So basically, you'll need every single neuron in your MLP to be connected to every single pixel, which means you'll have a lot of weights in your model. Or think of your weight matrix W, so it will have a lot of columns. Okay. So when you have a lot of parameters, you greatly increase the risk of overfitting. Like we saw previously with MLPs, they can learn these kind of nonlinear decision boundaries, and you can see that it doesn't really matter if you have one hidden layer and more neurons, or if you have more hidden layers and less neurons. You're still increasing the number of parameters, so you potentially you're potentially more likely to overfit. Okay, so that's one problem with just having a lot of parameters. Besides that, it's harder to train, obviously. But the more crucial issue is that fully connected layers are very sensitive to translation, which means, for example, if you take your image and just create a feature vector from it, then what you're basically saying is you're dependent on specific things being in specific locations in the images, and which is not really relevant for vision. When you think about vision, you want to detect a face. It doesn't really matter if the face is in the middle of the picture or in the top left of the picture. You still want to understand that this is a picture of a face. Even if you move slightly by a few pixels, such an FC fully connected layer will have a problem with that, because you're training your parameters to kind of depend on what exactly is in each pixel. Okay, so those are the kind of limitations. Okay, but we still want to use these kind of deep networks because of their nonlinear ability to learn features from our data. Okay, so that was kind of the background and motivation for why MLPs are not good enough for images, and what we'll show now is a different kind of architecture, convolutional layer. So I'm gonna show it two different ways, the convolutional layers. I'm gonna show kind of a structural way to understand it, and then a filter-based way. Kind of two different ways to view the same thing. But basically, when it's implemented actually behind the scenes, it's not exactly either one of those. It's just implemented with matrix multiplications. It's more like the second thing I'm going to show, but this is just to understand it conceptually. So let's start with a structural view, like how to think about its structure. So a convolutional layer would be similar to a fully connected layer, but we have three key differences. So first of all, instead of each neuron being connected to everything from the input layer, each neuron now will be only connected to a small region of the input. Okay, so if you have an image, then each neuron will only be connected to a small window from that image. Okay, and instead of a 1D grid of neurons like we had in the MLP, where we saw our model is kind of like a 1D stack of neurons that are all connected to the previous. So now we're going to organize our neurons in a 3D grid. Okay, and crucially, if neurons are at the same depth of our grid, then they will share the same weights, the parameters W and B. Okay, so in this image, you can see an example of a convolutional layer. So each circle here is a neuron. The neurons with the same color have the same parameters. They all share the same matrix W and bias term B. Okay, and each of them, as usual, is just a neuron that computes an affine transform, does some nonlinear operation element-wise on that, and creates one number. Okay? Good. So a consequence of this way of viewing it is that these layers operate and produce 3D tensors or volumes. Okay, so they work on an input 3D tensor, which in the case of an image, for example, if this is my image, then I have, for example, 1,000 pixels by 1,000 pixels by 3 color channels. Okay, so it's a 3D tensor, and I'm converting it to some other 3D tensor. The way I'm doing it is by making each of my neurons spatially local, but it looks on the full depth. So for example, here is a neuron. Like I said, all the neurons that are on the same plane with this red neuron will also be red, so they'll have the same parameters. They will each look on a different window, but they will see the whole depth. Okay? Any questions? All right, so that's how kind of structurally to see it. So, okay, so that, I hope it's clear now why you get 3D volumes out of it, okay, and why it works on 3D volumes. Okay, so that's kind of one way to see, yeah.
You mentioned that a drawback of MLP is that it's dependent on translation. Now, when each neuron looks at the same width and height, it's also sensitive to translation.
Okay, so the question is, why is this not sensitive to translation? The neurons that are on the same, for example, each of these red neurons, they don't look at the same window from the image. They look at different windows from the image, but they share parameters. Okay, so each of these neurons computes the same function, but on a different part of the image. Okay, so you can think about it like it's looking for something. We'll see what later, but it's looking for something, but in different parts of the image. Okay, so that's why we have this spatial organization where we have a 2D plane of neurons with the same parameters. Okay, so each of those neurons in the same plane are looking at different parts of the image, but they have the same parameters, so they're doing the same function. And then we have a bunch of these different functions. We stack them. That's the depth element. Okay, so that's why there's different colors when you go deeper, because you have different parameters, so you're computing a different function. So you have a bunch of different functions that you're computing on different areas of the image, but you're doing it very locally, small windows. Okay. Okay, so just to make it clear, again, you look at a spatial window that might be small, like 3 by 3, but you're looking at the whole depth. So if you have 3 color channels, it will be 3 by 3 by 3, what you're looking at. Okay. Now the other way to look at the same thing is a filter-based view. So we can look at it like this. Let's say we have this color image. Okay, so it's again a 3D tensor, and let's say we have these 6 different filters. Okay, these are filters. They're 3 by 3 by 3 filters because there's a 3 depth here. So let's say I'm sliding each of these filters over my image, doing a convolution between this filter here, this white filter, and my image. Then I will get a 2D plane here, because each position that I position my filter on my image will give me one number. Okay, so the other way to look at it is I have a bunch of filters. I have, in this case, 6 different filters. I'm applying all of them to my image, and I'm just stacking the results into this cube, okay, 3D tensor. And kind of, if you haven't seen convolutions before, then this is just like a small visualization of a single filter. What it can do, it can basically highlight different features from an image. If I take, for example, this 3 by 3 filter, and I convolve it or move it on this image here, okay, then it will basically, it gives you a maximal response when you have a diagonal edge. So for example, you have a high response here and a high response here, but in other places you get lower responses. So that's kind of one filter, but again, these filters are actually also depth-wise. Okay, so that's the other kind of way to view it. Like I said, when it's actually implemented, then it's not exactly implemented like this. It's more, it's based on these filters, but using Toeplitz matrices and stuff like that. You'll see it in the lecture if you haven't already watched it. Okay. So, all right. Like I said, we take our input and compute slices, these depth slices. Each of them is a result of a different filter. Okay. And we also call them feature maps or channels. So given an image, for example, we can compute any number of feature maps from that image using different filters that each filter is convolved on the image. Okay, is it clear so far? All right, so let's start defining more specifically what convolutional layers kind of are made of and how to define them. Okay, so let's say we have an input tensor of this shape. We have C-in channels, for example, 3 channels, like color channels. H-in and W-in are the dimensions of our image. Okay, and we'll define the following parameters, which I'll explain in a moment. Then this constitutes enough for a convolutional layer. So let's say this is our image. Let's define some number of kernels, or kernels is also a different word for filters. Okay, so we need at least one filter. We need a spatial size of each filter. This is spatial. Again, it doesn't affect the depth. We always operate on the whole depth. So this will be, for example, if f is 3, then we have a 3 by 3 filter, but it always operates on the whole depth. So it's 3 by 3 by the depth, by C-in. We define a stride, which is kind of the distance that we move our filter each time. I'll show it in a second. We define a padding, which is how many zeros, how much we pad our input, because it allows us to move our filter over the image, not just on the image locations itself, but also outside our image. I'll show you why in a second. And there's another kind of parameter called dilation, which is best explained visually. So let's look at kind of a visualization of this. All right. So just try to focus on one of these. It's easier. So for example, here you have your blue input. This is one channel of an image, for example. The gray area is a convolutional filter. Okay, and the green is the output. Okay, so in all of these cases, we use a 3 by 3 filter, which means f is 3. Spatial extent of our filter will be 3. Okay, so for example, let's look at this image here. We just take our filter, we move it along or convolve it with our image, each time we basically do an inner product, just multiply and sum, and we get one number out, which is the output. Okay. In this case, for example, we added padding. Okay, so here in this leftmost case, p is 0, and here p is 1. Padding is 1. So as you can see, we added zeros around our image, so now we have more places to put our filter when we convolve. Okay, in this case, for example, we create an output of the same size, spatial size. Here we have strides, which means we don't move our filter 1 pixel at a time. Okay, we jump it 2 pixels at a time. So that's why even though we have padding here, we get a smaller output size. Okay, and this is an example of dilation. Dilation means we add spacing between the kernel elements to see a larger part of the input. Okay, so again, there are combinations that preserve the spatial extent of the image. For example, this combination here. Any questions about that? Okay, great. So basically, just before I show you this, you can kind of intuitively grasp that, for example, the more you increase f, the spatial extent, the smaller the output will be. Okay. Conversely, the more you increase padding, the larger the output should be. You have more places to put your filter. If you increase the stride, it should make the output smaller. If you increase dilation, it should also make the output smaller. That's kind of intuitively. So from those, you can kind of work it out, but this is from the PyTorch documentation at least, that this is the relation between the input dimensions and the output dimensions. As you can see, for example, padding increases your output dimension, while increasing f would reduce it, and same for s, same for the stride. Crucially, it's important to note that the output number of channels is always the number of filters. Okay? Is that clear? Why that is? Yeah, again, because for each filter, we have one 2D plane that we're generating. Okay, so the output number of channels will be always same number as the number of filters we had. All of these parameters just define the spatial extent, not the depth. Okay. Good. So anyone want to try to guess how many parameters we'll have in a convolutional layer? Okay, let's think. We have k different kernels or filters. For each filter, sorry? No, it's not. It wouldn't be dependent on the image size. So H and W, no. But what we do have is k different filters. What's the size of each filter? F squared times the depth. All right. Exactly. So this is the number of filters, the parameters. Sorry, the number of parameters in our convolutional layer. So we have k kernels. Each kernel is of size Cin times f squared. F squared is our spatial extent, and this is our filter depth. Like I said, filters always operate on the whole depth. All right, so this is our number of parameters for our kernel, and then we have a bias term, and we have k times that. So for example, now let's return to our first example where we had a 1000 by 1000 by 3 image. So let's say we have 10 kernels of size 5 by 5. You can just plug in the numbers. You can see one convolutional layer operating on that image will only have 760 parameters. Okay, and this is a result of the weight sharing. Okay, since we share weights between neurons on the same layer, which is basically what we're saying is we only have 10 different sets of weight, 10 different kernels of 10 different sets of weights, we get a low number of total parameters in our network. Okay. Let's keep going. Let's see an example now, how to implement just the conv layer now, not the whole network. Okay, so I'm just loading a data set here. This is CFAR10. Doesn't really matter. I just used it because it has 3 color channels. All right, so let's take an image from this data set. So first thing, I just took the first image. The first thing to notice is this operation here first. Unsqueeze, it just adds another dimension to my tensor. So this would be my image, 3 color channels, 32 by 32 is the spatial extent. I added 1 dimension for the batch dimension. If you started your homework already, you'll probably be familiar with this. The convention is always that the batch dimension is first when you have a data set. So the PyTorch layers are built to work with batches of data. So if you have just 1 image, you just add one, put it in a larger tensor with just 1 element, which is what I did here. Okay. Okay. So let's just define quickly a function to count the number of parameters in our model. We saw this last time. Okay. Remember, parameters returns a generator returning the tensors. Okay, so we just count the number of items in each parameter tensor. Sorry. Okay, so here we go. Let's define a conv2d. So conv2d is a module. It derives from nn.module, which we saw last time. It's one of the built-in modules in the nn package. You can see, for example, here what I'm defining are my parameters, the same parameters that I showed you before with the animations. So this is the input number of channels, for example. So I'm taking just the size of x0. The first element is the number of channels, which is 3 in this case. I'm just saying that I want 10 output channels, so this is also my number of kernels. Okay, and here I'm defining how much padding I want, kernel size of 3, and what stride I want. So if you remember from our animation, these parameters should keep my spatial extent similar. Okay, so let's just calculate the number of parameters in this layer and apply the layer. As you can see here, I'm just applying the layer to my image, just calling it like a function. Remember, this calls the forward function of your model class. Okay, so this is just the forward pass. Let's see what we get. So we have 280 parameters. First of all, let's see if that makes sense with what we said before, right? So we have 10 kernels, okay, and we had a kernel size of 3, so we have 3 squared, and we have 3 input channels because it's a color image, okay, and we have a bias term. Okay, so that should be it's 27 plus 1. Yeah, okay, so it makes sense. So first of all, you can see it's defined like we said, no surprise. So this is our image shape again. And this is the shape after the first conv layer, okay? So make sure you understand why this is happening. So first of all, the number of output channels is just defined by the number by this parameter, the number of convolutional kernels that you want. You just say so. So this just tells this class how many W and Bs we have, how many tensors of W and Bs we have. Okay, and these parameters define the spatial extent. So like I said before, this combination of kernel size 3 with padding 1 and stride 1 maintains the spatial extent. That's why we got the same output size here. Okay. Now let's create another conv layer. So now we're defining our input channels as 10 because that's what we had for an output before that. Okay. We'll just because we'll say we want 20 output channels, and this time we say no padding with a larger kernel and a larger stride. So we expect the spatial extent to decrease. Okay, no padding now and a larger kernel and a larger stride. So let's see what we got. So now also, first of all, we have much more parameters. Okay, because we have 20 output channels and a much larger kernel. Okay, so makes sense. Again, the output dimension of this operation, conv2 of conv1 of the image, has 20 output channels because that's what we asked for, and a lower spatial extent because of the parameters that we defined here. Okay? Simple. Okay. This is a good point that we'll see later. We never specified the size of the image actually. We just said how many input channels there were here. We never said that it's a 32 by 32 image, okay? So we'll see later why that matters. Okay, so let's talk about a different kind of layer which is used usually in convolutional architectures, pooling layers. So we saw that we can reduce the spatial extent with playing with the stride and the padding. But another way, which is kind of the more classical way, at least in older papers, was to do it by using pooling. So what's pooling? It's just a layer that has no trainable parameters. There are no parameters, just hyperparameters. And you define the spatial extent and the stride and what to do. So it basically splits your image into these regions. For example, here f is 2, so we have 2 by 2 regions. And if the stride is 2, then they don't overlap. And we just do some operation and return one number. So for example, if we do max pooling, then we'll just return the max value from each of these different 2 by 2 regions from our image. Okay, so it would do a factor 2 downsample. Okay, it's possible to also do this with regular convolutions. This is kind of the more classical CNN way. Okay, so first question is, why actually do this? Why would you want to reduce the image size? Any ideas? Less computationally heavy? Less operations? What do you mean less space? For the image to take less space. So total number of parameters. But the total number of parameters depends on the number of filters and their size. So redundancy. Okay, that's close. Okay, so exactly. So we want to try to capture more. So yes, there's a computational element, but the real kind of intuition is that you want to kind of, as you go deeper, capture more of the input. So it's called increasing the receptive field. So as you go deeper, you want the output of your neuron to depend on larger parts of the image. So kind of also you can intuit it by thinking like at the end we want just kind of a classification score. So we have to somehow combine the results that we get, the filter results that we get in each layer. We have to start combining them until we get some kind of score. So that's kind of the looking at from the end. But also thinking about combining is you can understand that you're increasing your receptive field in the way that each neuron that's deeper than the previous one depends on more of the input. So if you would change a larger and larger region of your input, it would affect deeper and deeper neurons. And kind of the intuition behind it is that it allows you to learn a hierarchy of visual features. So one of the things that there are various papers that show is that in the beginning, the less deep layers of CNNs, you can see kind of filters that are learned which kind of detect very simple features, for example, lines, diagonal lines, horizontal lines, and stuff like that. And when you start combining them, you can say, for example, if you have a diagonal line going up and a diagonal line going down, it might correspond to kind of a higher level feature, for example, an ear. So you might see that in deeper parts of the network, there are neurons that detect specific features of images that are higher level. For example, there's a neuron that detects eyes, or there's a neuron that detects ears, and things like that. That's kind of the intuition behind it. Okay. So just quickly, let's show an example of the pool 2D layer. So here I'm doing max pooling, just defining the same parameters that I showed you, kernel size and stride. I'm taking my two conv layers, okay, applying them. So I had this spatial extent, and after that I'm doing pooling. Okay, so if the kernel size is 2 and the stride is 2, then I'm reducing my spatial extent by half, because it's like in the image that I showed you. We have 2 by 2 regions that we're doing max on, and they're non-overlapping. So okay, so that's why we get 7 by 7, and it doesn't affect the number of channels at all. It just works on the feature maps individually. All right, so let's talk briefly about architectures, what it means. Okay, so the way to kind of build an architecture to, for example, do image classification is to take some convolutional layers, add some non-linearities between them, because it's still a linear operation. And everything we saw, except for example the max pool, it's just linear operation. But what you can do, you can add non-linearities like ReLU between your layers, and what that allows you to do is generate features from your images, and on top of that you can do a classifier the same way that we saw, for example, in the previous tutorial, where we use a fully connected layer to combine the features, and then do a softmax to produce class probabilities. Or we don't do a softmax, we just use the scores. Okay? So, for example, here's an example of a bunch of architectures. This right one is also called VGG. It's one of the contestants in ImageNet, I think, in 2015. As you can see, it's kind of composed of recurring blocks. We have an input. You do conv, and this conv is actually conv and some nonlinearity, like conv value. You do pooling. You do that a bunch of times. Okay, maybe you do more convolutions, like more deep convolutions, and in the end you do some kind of fully connected layer and softmax. So again, the purpose of this last part is after you have your convolutional features, which, like I said, you reduce their spatial extent to combine them into higher level features. You take all these high level features and train a classifier on top of that. So you start combining them with the fully connected layers, and then create your class probabilities. Okay, so that's kind of the basic idea of building an architecture, but there's kind of lots of details here. So, like I said, basically where it says conv, it's actually conv value, and there's many other things that you can add. So, for example, you still need to define as part of your architecture the size of your convolutional kernels. Okay, so if you have larger kernels, you're increasing your parameters, but you're also getting a larger spatial extent each time. The number of consecutive convolutions, so maybe you want to do, for example, like here, you're repeating blocks of 1, or maybe you want to repeat blocks of 3. So these have different kind of trade-offs, both in the number of parameters and in the representations that they can learn. And other kinds of layers that you'll actually talk about in the next lecture. Batch norm and dropout are kind of ways of either training better or faster, or increasing your model's generalization, which means it will perform better on your training set. And the other two things here are pointwise convolutions instead of the fully connected, which we'll see in this tutorial, and skip connections, which we'll also see. So there's a lot of hyperparameters that define your architecture, but that's the basic idea. So just briefly, this shows kind of the results of different architectures on ImageNet, which is a large classification challenge containing about a million images, I think, with 1,000 categories. So in 2012, the first deep learning model kind of won the ImageNet contest. It was called AlexNet. It had only 5 convolutional layers. It was based on LeNet, which we'll see in a second. And you can see kind of as the years go by, usually the scores just go up with more advanced deep learning models that have more and more layers and more advanced features. So this actually shows each circle here, the diameter of the circle is the number of parameters. So you can see kind of the really huge models don't necessarily perform better than the state of the art. Okay, that's just kind of to get some feel for results. Now let's dive into the code a bit more. Okay, so let's look at how to implement a convolutional architecture with PyTorch. Okay, so what we're going to implement is an architecture called LeNet. It's from '98. It was shown for classifying the handwritten digits in MNIST. So again, we'll see this problem, but we won't actually train it. We'll just show the implementation. Okay, so the LeNet model starts with a 32 by 32 input. Doesn't really matter, but here in this image, it's just one channel. Then you have 6 convolutional kernels, creating 6 feature maps, and changing the spatial extent to 28 by 28. So you can calculate and see that you need a 5 by 5 kernel for that. Then you have a pooling layer, which keeps it at 6 channels, but reduces the spatial extent by 2, so we get 14 by 14. Then we have 16 kernels in a convolutional layer, and again we reduce the spatial extent, so again it's a 5 by 5 convolution. Then we have another pooling, and then we have 2 fully connected layers. Okay, that's what we get here. So the first fully connected layer computes 120 features, then 84 features. And then we have 10 classes, finally, because we're trying to get a class score for each digit. So the output size should be 10. Okay, so that's our architecture. Let's implement this. Okay, so let's go.
How do you flip the S4 and the C5 values?
Sorry, I couldn't hear you.
The S4 and the C5, how do you flip between the S4 and the C5? How do you flatten the tensors?
How do you flatten the tensors between S4 and C5? Great question. You'll see it in the code in a sec. Okay. So let's start. So first of all, again, we're using this NN module kind of base class for our modules. This is the base PyTorch module. It allows you to define your own layers. In this case, we'll build our LeNet out of two parts. So first we have our feature extractor, and then we have our classifier. Okay, so the feature extractor part corresponds to all the convolutional parts. So up to the S4, that's our feature extractor. We have features generated by our convolutions. Then we have our classifier, which is the fully connected layers. Okay, so the feature extractor part is built from a sequence of conv2D with input channels, which is some parameter that I can define. We have 6 output kernels and a 5x5 spatial extent for each kernel. Okay, then we just do relu, max pool 2D2, which means like you saw in the previous example, 2 by 2 and a stride of 2. Then another conv2D. This time we have 6 input channels because that's what's the output. Converted to 16 channels. This is number of filters, and again 5x5 filters. Again relu, and again max pool. So by the time we get here, we have our convolutional features. Wrap the whole thing in a sequential, which means apply these layers one by one after the other. That's our feature extractor. Then classifier. So first thing, we have a fully connected layer. Okay, so where does this come from? Any ideas? Dimension, yeah, okay. So it's a spatial dimension times the number of kernels. Let's look at LeNet again. The last part here has a 5x5 spatial dimension if you implement it correctly, and you have 16 channels. So the number of total activations in this 3D tensor, okay, would be 16 by 5 by 5. We're putting this as an input to an MLP layer, and we want 120 output activation. So we have 120 neurons in our MLP layer here, this linear layer. Then we pass it through a relu. Then another linear layer, which is 120 to 84. That's just the numbers that were in the LeNet architecture. And then another one from 84 to 10, because this is our class scores. Finally, we have 10 class scores, one for each digit. Okay? Then, regarding the question that was asked, how to flatten it. So during our forward pass, we just use these two parts of our model. So first we apply the feature extractor to our image. We get features. So this is a 3D tensor 5 by 5 by 16. We just flatten it. Okay, this is like a reshape. Flatten it to one long column, and then we apply our classifier, which is a bunch of fully connected layers, to this column to calculate our 10 class scores. Okay, is that clear? Good. I'm not showing the softmax here. This is just the scores. If you want to get probabilities, you can add softmax. Yeah. Okay, so let's create an instance of LeNet here. So we created an instance and we just printed it. So since we're using NN module, it just automatically prints all the parts of our model, all the inner modules. So we have an inner module called the feature extractor, which is a sequential, and you can see the sequence of layers that it performs. So conv2D, 3 to 6, and so on. Okay, you can see all the layers, then the classifier. And what I did here, I applied my network on my first image. Okay, so the output is a tensor. You can see it has 10 elements, which is what we want. Okay, so just a 10 element, 1 by 10. Okay, Great. So now that you have that, you can just use this module and train it exactly like you saw in the last tutorial. Last tutorial, we created a module from scratch, called it an MLP, and then we used built-in things from PyTorch like the optim package and the autograd functionality. So you can just take this network object that you created and train it exactly the same way, and you'll have trained the convolutional network. Okay. So I'm not going to show the training of MNIST again. Okay, so let's talk about a different kind of architecture, fully convolutional network. It's not very different, it's just using only convolution. So the first question is that notice that we never actually specified the input image size. So we had images 32 by 32, but we never specified that image size. So the question for you is, does that mean that we can use this network that we just implemented on any image size? Why not? Exactly. So the answer was because of the fully connected layers at the end. So we calculated by hand, if you remember, we calculated this number. So this does depend on the image size. It depends on the image size and the configuration of these layers that reduce the spatial extent with the padding and stride and so on. So yes, the answer is no. Right now we can't. Let's try. If we take here I'm just taking a random tensor with 3 channels and it's twice the size, so it's 64 by 64. I'm trying to run it through my network and I can't. It doesn't work because when it reaches the MLP layer, then I have a mismatch of the matrix sizes. The W matrix of the MLP layer can't be multiplied by what I get with my long vector that I created with the reshape. Okay, so what we can do, what can we do? We can replace them with convolutions. Okay, so instead of having a fully connected layer at the end, let's have more convolutions. Okay, let's see how to do that. So let's create a LeNet fully conv. Okay, this uses our LeNet. So we're just deriving from the LeNet class that we implemented before, and we're just overriding the init function. So we still have our feature extractor part from before, but we're just overriding the classifier part now. So remember that we had a volume of 16 channels, 5 by 5 spatial extent. So now we'll change our classifier. Instead of a bunch of fully connected layers, it will be a stack of convolutions. Okay, so we have 16 input channels, and we want 120 output features. Okay, and we're using 5 by 5 here. So any idea why are we doing that, and what would be the output here? Okay, so let's draw it a second. So we have 5 by 5. Okay, we have 16 channels depth. Okay, hope I can draw it correctly. That's our 3D tensor. So what would be the output? Yeah, okay. 1 by 120. Why? We have no padding or strides. We take a 5 by 5 filter. Remember that the filters always operate on the whole depth. If you take a 5 by 5 filter, it's 5 by 5 by 16 actually. So you take 120 different filters, but each filter fits only once in this volume. Okay, so what you will get is 1 by 1 by whatever number of filters that you had. In this case, 120 filters. That would be your tensor. Okay, so it's similar to the fully connected. I'm just taking all the picks, all the activations in this volume, and applying one and just multiplying them once with each filter, because the filter can only fit one time. So then I'm getting my 120 activations. Then I'm doing 120 to 84, 1 by 1, because that's what I have now. So I'm just taking 1 by 1 by 120 filters. Okay, and then 84 to 10, same idea. That would give me, at the end of this process, I would have 1 by 1 by 10. So it's not exactly the same shape as before, but it's the same number of class scores. Okay, so no need to reshape now. I just take my features and apply my classifier now because it's convolutional. Okay, so let's do that. Let's see this is our network. Let's take a larger image. This is my large image. Okay, and apply my LeNet fully conv on it. So you can see for the original image, I got 10 channels, one by one. So this is the 10 class cores. So now I got 10 channels, but I got a 9 by 9 spatial extent. So any idea what's the meaning of this 9 by 9? So now I used the larger image. So instead of getting a 1 by 1 by 10, now I got a larger 3D tensor by 10. So what's in there? Okay, so one way to think about it is just think about your whole network as something that you can slide over the image. And at each point that you can fit your network on the image, you get the 10 class cores for that location in the image. Okay, so a way to see it is that it's a spatial classification map. Instead of getting just 10 numbers for the whole image, now I get 10 numbers for different locations in the image. So it's like at each location, it gives me the different probabilities of classes in that location. It's like taking your whole model and just thinking of it as a big convolutional filter that you can move around. So that would be a fully convolutional architecture and what it means to actually do it. What do you mean if I would add max pooling? Here? If my goal is to just detect whether there is a cat or not, just classify it, then maybe. But in this case, it's both a cat and a dog. So this image kind of it doesn't fit like one class. But the idea is that a region of the image does. So maybe you can detect if my classifier would be if I had two different classes and one of them was dog and one of them was cat, then I would get some kind of heat map here also that would show it's a dog. So I could use that however I want. Depends on the application. Okay, so now quickly let's show residual networks. So we saw that deeper is better, okay, for image-related tasks because we can learn hierarchical features. But the problem is that when you go deeper, this actual meme was from the Inception paper. That's actually kind of a name for a model now. So the idea is that the problem when you go deeper is that you have a problem both to converge and also to optimize. So you have the vanishing gradient problem, which again will be hopefully addressed in the lecture. And just by going deeper, you have more and more parameters that you need to optimize over. But if you think about it, then adding another layer shouldn't really hurt your performance. I mean, if your optimizer was really, really good, just adding another layer, it could always learn like an identity map. So it shouldn't really hurt performance ideally. If you had the best optimizer and could actually somehow find an optimal, adding as much layers as you want shouldn't hurt. But actual results say otherwise, that when you add more layers with a naive approach, then you do get, this is from the ResNet paper, they showed at least that when you add more layers, you do hurt performance. So the idea is to, on one hand, try to add more depth to learn kind of more higher level representations, but find a way to optimize it. Okay, and the idea behind ResNet is to create these blocks with skip connections. Okay, so we have here, for example, a group of two convolutions. And what we do is we add this skip connection here. And like I said, intuitively, you can think about it that you always have this identity map, and now what you're learning is what to do, what to change. So what to add to X, to this identity map, to change. So you can always learn an identity map by just not doing anything. It's much easier to learn an identity map now than it was if you just didn't have this skip connection. So that's kind of the intuition, why do a residual mapping? So this is called a residual. And also, from an optimization perspective, even though the network would be deeper, you have an ability to get your gradient flowing backwards through these skips. Okay. So I don't know if I'll have time to go into the code, but I want to show you how to implement ResNet 18, which is an 18-layer ResNet. You can see here the architecture. It starts with a 7x7 convolution of stride 2. Then we have 3x3 max pooling, and then just repeat 3x3 convolutional blocks, kind of with more and more channels. Okay, more and more kernels as you go deeper. Okay. So I'll try to just take one more minute. I'm just going to show you kind of high level how to structure it, and you can also run it for yourself. So I implemented here separately the ResNet block, which is this part. Okay, this is one single block, and then the whole network. So you can see there are two parts in this block. There's the main path and the shortcut path. The main path is just taking two convolutions, two conv2D layers with a fixed kernel size, because that's what's in the table that I showed you before. And the first stride can be different, but that's just a parameter. Okay, so just two convolutions. And the shortcut path is kind of where there's a small trick that you need to do, because you can't really do this operation, add the main path with the shortcut path, if the dimensions don't line up. So you kind of need to check if the number of output channels is different, or you have a stride, then you do need to somehow change your spatial extent or your depth. So the kind of way to overcome that is just to add a 1x1 convolution here, just to change the spatial or depth. This would change the depth if the output channel is different. Okay, and it's 1x1, so it doesn't actually look at any spatial structure. Okay, so then you just add the shortcut to the main path and apply the ReLU as exactly like in the diagram. Okay. Batch normalization, you'll cover it in the next. It's a way to normalize and make training faster, basically. Normalize the inputs to each layer. So it's out of the scope now, but you'll see it in the next lecture, next week actually. Okay, and the ResNet implementation itself, there's nothing really interesting here beyond what you've seen. Just create the input part, which is the 7x7 convolutions. Do that, and then add 4 of my ResNet block groups. So you can see here, I'm defining the number of channels for each group, and then I'm creating a sequential of 2 ResNet blocks. Okay, doing that in a loop, and then I get my blocks. And in the end, there's just pooling and fully connected. Okay, and the forward pass is applying the input part, the fixed part, and then for all of my groups, I'm just running the forward pass of that group. Okay, that's it. So you can hopefully dive into this a bit in more detail by your own. Okay, if you run it, you can see kind of the whole 18-layer architecture. When you print the network, it's kind of deep. But again, you can just run it and train it like any other PyTorch module. Okay, here I'm running it on a larger image, 224 by 224. You can see my output is 10 class cores again. So this is a much deeper network. Same ideas. Okay, thanks.